These are the notes on organic chemistry, where we will continue to learn about molecules and covalent bonds. So organic chemistry kind of has a bad reputation. A lot of people know it as OChem. It's often considered one of the harder classes to take in college, one of the harder science classes. And that's just because there are so many chemicals that are organic. And if you really want to know all of them, well, that's crazy. That's heavy duty. But we're just going to do a simple exploration of organic chemistry on a high school level, so don't get too freaked out if you know its reputation. So organic chemistry is the study of molecules built around one very, very special element. What element am I talking about? That guy, who is that? Oh yeah, carbon. It's the study of molecules built around carbon. These are the molecules of life. These, in fact, are the largest molecules that we find in the universe. All of them are built around sort of carbon skeletons, okay, if you want to think of it that way. If you recall, the periodic table is divided into major groupings. Out of the 118 elements, 92 of them are metals. What percent was that again? 78%. 20 of them were nonmetals. Well, that's 17%. And 6 of them are metalloids. That's about 5%. So notice that most elements, again, are metals. That's important. Metals don't form molecules, do they? Very rarely. And they will only form them with nonmetals. Nonmetals left on their own, those are the ones that will form molecules. So it is the nonmetals we must look to, those few elements on the periodic table that actually will make molecules when put together, that we need to focus on when we want to learn about larger molecules. And notice, obviously, carbon is one of them, but carbon is right on the edge. Notice where the nonmetals are off to the right, except for hydrogen, they're off to the right. Carbon is the very last one over, kind of sticking out way out on its own. So there is a way of thinking about it that carbon just barely made it into the category of nonmetals. So carbon is a nonmetal because of the kind of bond it forms. That's one of the main reasons. But it is a solid at room temperature, kind of like metals. And in some of its forms, it will conduct electricity. In fact, it is the only nonmetal that is capable of conducting electricity. By the way, it normally doesn't. It just has to be in certain forms. In certain forms, it will, like in graphite. Now we come to abundance. Don't forget about this. Some elements are really abundant. They're everywhere. They're ubiquitous, like hydrogen. You can't get away from hydrogen. And then in the universe as a whole, there's a lot of helium. And then there's still a lot of oxygen. Okay, so notice that each one is getting smaller. That means there's less and less and less of it. Well, eventually we get to carbon. Carbon isn't that far along this list. It's not way down the chain with one of those really rare elements, really scarce elements, I should say. So carbon is fairly abundant. It's not the number one. Let's look at its ranking. Oh, before we do that, let's look at carbon in the human body, or in pretty much any living thing. Carbon has an even higher ranking in the human body. It's much, much closer to the front of the list, okay? Because after you take out the water, a lot of what is left of us is actually made of carbon, and water is made of hydrogen and oxygen. So if we look at the ranking of elements, we've discussed this before, obviously, by far, without a doubt, hydrogen is number one. And partially that's because any given loose proton is considered hydrogen. That's part of the reason. But anyway, hydrogen, very extremely abundant. After that, helium is number two. Oh, that's funny, because on the periodic table, hydrogen's atomic number is 1, and helium's atomic number is 2. So that's kind of cool. Then we get oxygen, neon, nitrogen. Well, those don't match up. Oh, but wait, then we get carbon, which is number 6. Isn't that cool? By coincidence, carbon is number 6 most abundant, and of course, it is element number 6 on the periodic table, atomic number 6. So notice that all of the elements down to carbon are nonmetals. So if carbon is going to bond with an element and it's going to make a molecule, well, it's probably going to be mostly things that are on this list, especially hydrogen and especially oxygen and nitrogen. Those are the ones that carbon is going to bond with. Well, it's not going to bond with helium, right? It's not going to bond with neon. Those are noble gases. But it is going to bond with the other nonmetals that are not noble gases on this list. Also look at the Lewis dots. Look at carbon's position if we look at valence electrons. Well, of course, the ones on the left all have 1. The ones on the right all have 8, correct? So that means the ones on the left, well, they can form 1 bond, can't they? The ones on the right, well, they can form no bonds, the noble gases. But the group next to them, oh, the halogens starting with fluorine, well, they have 1 unpaired electron. Notice the ones starting with fluorine at the top that have 7 valence electrons. But only one of them is unpaired. Only one of them can form a bond. That's 1 bond. And then if you move slightly over to the oxygen family, well, then now that can form 2 bonds. And if you move slightly over to the nitrogen family, well, that can form 3 bonds. And then what about the carbon family? Now we're up to 4. Keep moving over to the left. And boron, well, boron got disowned, so we call that the aluminum family. That family can only form 3 again. Then it drops down to 2 for beryllium and 1 for lithium. So really, carbon is where you get the maximum number of unpaired valence electrons. It's really where you have the greatest chance for forming a whole lot of bonds. And that is why carbon makes so many of these giant molecules, because it turns out if you can build in 4 different directions, well, then you can just keep going and going. You can just keep going on and on and on and on, almost infinitely, theoretically. Okay. But you could say that about anything in carbon's family, right? Look below carbon. Isn't silicon same thing? Isn't germanium same thing? Tin and lead, same thing, going down carbon's family? Well, yes, but there's one important difference. Carbon is the only member of the carbon family that is a non-metal. Silicon is a metalloid, okay? Germanium is a metalloid. Tin and lead are metals. Therefore, they don't form molecules generally. It's less likely that they will form molecules, at least, according to the rule of thumb, right? So carbon is capable of making the most bonds, and it's a nonmetal. Boom! That is why carbon is so important to the big molecules and the molecules of life, organic chemistry. So remember that because carbon is a nonmetal, the rule of thumb on the right, the green one, applies. 2 nonmetals form covalent bonds. That's the rule of thumb, and carbon definitely does that, almost always forming covalent bonds. Very rarely ionic bonds, and almost never metallic bonds, of course. So that puts a lot of carbon-based compounds into the molecule club. Because if you've got carbon in your compound, it's going to make covalent bonds, which is a big plus if you want to be a molecule. The only thing that could rule you out is if it winds up making a polyatomic ion. But carbon doesn't make as many of those as some things do, but it does make some polyatomic ions. Generally, carbon is found in many, many molecules. And you can see 2 of them represented here in the molecule club as methane and carbon dioxide. 2 very, very common forms of carbon. So when we're talking about carbon, you could picture like what's left over after you've burned a block of wood, let's say, on a fire, and the process of burning has removed all the water from it and a lot of the rest of the wood, but a little bit is left over, and a lot of times that's the carbon. So like think of the ashes left behind after burning a piece of wood. Okay, that's often very, very much carbon. And carbon, of course, has those 4 valence electrons, which means it can form a lot of different possible structures. One thing that it forms is what you often write with in school, in a pencil. Well, a lot of people call that lead. Well, it never was lead, by the way. It is actually what we call graphite. There's a chunk of graphite above the pencil, but if you take a little core of graphite and stick it between a piece of wood, then it rubs off very nicely on a piece of paper, and we've been using that for hundreds of years. So graphite is very, very soft. So carbon can form things that are super, super soft. On the other hand, strangely, carbon can also form the hardest material that we know, which of course is diamond. There's a pure diamond structure forming in a rock there, a pure diamond that has grown volcanically. Diamond is actually the hardest naturally occurring substance that we know of, and that is also made of pure carbon. What a weird mix that carbon can make something super soft, rubs off right onto paper without cutting through the paper, and then something super hard like a diamond that'll cut through any other material. Okay, will cut through quartz even. Strange. One reason carbon can do this is that it likes to arrange itself into hexagons. Now, it might not seem like that makes sense based on the tetrahedral, but just bear with me here. Bear with me. Carbon often forms hexagonal patterns, but these patterns don't stop there. They are kind of ongoing. They repeat on and on and on. And this is what we would call, nowadays we have a new name for this. We'd call this a sheet of graphene. That is a recently identified allotrope of carbon, which is just one thin layer of these carbon hexagon structures. Okay, well, it turns out this layer is actually pretty tough, but it is barely connected to the layer on top of it, which is barely connected to the layer on top of that. And so because of that, they can easily be slid apart just by pushing a little bit of force on them, which is kind of what you're doing when you're sliding it on your paper. You're putting just a little bit of force, sliding off layers and layers of that carbon hexagonal structure, and that is what we call graphite. So now they have a name for one layer of graphite. They call it graphene, and they notice that when you just have one layer, you have different properties. By the way, the guy who won the Nobel Prize for that, I heard an interview with him, and the way that he removed a layer of graphite was he took a piece of tape and he stuck it onto the end of a pencil, and he removed one layer, and he called it graphene, and then he examined its properties. Boom, Nobel Prize. By the way, you get $1 million along with the Nobel Prize. It's not just the prestige that you get. You get a lot of money as well. In a diamond, on the other hand, the carbon is arranged very differently. It doesn't look hexagonal at all. In fact, it's very, very blocky, almost like it's a cube of carbon, locked in every direction. In a way, this is like an ionic compound, because ionic compounds are linked in every direction. But this one has covalent bonds in every direction, which makes it even far beyond the strength of any ionic compound. So ionic compounds are tough because they have so many bonds, but each of them are weak. Well, this has so many bonds, but each of them is strong. So imagine that is why diamond is the hardest naturally occurring material. So carbon is a nonmetal. Neither one of these two forms really appears metallic. Neither one has that metallic luster, even though diamonds can be shiny. They don't have what we call a metallic luster. And graphite does conduct electricity if you do it right. By the way, if you break off the eraser and if you sharpen down both ends of the pencil, that is an excellent conductor from one end to the other. We use that in some of our experiments, like electrolysis sometimes. And diamond is not a conductor because of the way the atoms are arranged. It is not a conductor. But carbon is definitely a nonmetal, decidedly nonmetal, because it forms molecules. And remember, metals don't, or at least they don't on their own. Some metals will be found in molecules, I must admit, when they are bonded to a nonmetal. So this brings us to the very first group of organic chemicals, and by far the most important group. In fact, you can think of all the other organic chemicals as just these chemicals wearing a hat. I'll talk about that later. These are called the hydrocarbons. So hydrocarbon, that's pretty obvious, right? They only contain two elements. What are they? Hydrogen and carbon. But this brings us to one of the aspects of organic chemistry that makes it so challenging. Organic chemists are never happy just doing things the way that regular chemists do it. They like to do things their own way. And one of the examples of this is they decided that instead of writing the less electronegative element first and the more electronegative element second, which is how we almost always write it in a regular chemical formula, they decided, no, let's switch it around. So hydrocarbons, even though they're called that, are written this way. The carbon is written first, followed by the hydrogen. And that's just, I guess, because of the importance of carbon. You got to give carbon respect, put it up front. I guess that's the most likely explanation. They also sometimes like to break it down into little chunks of the chain, and that's another reason that they do this. When we're talking about hydrocarbons, we have to learn the hydrocarbon prefixes. These have a varied origin. Some of them come from the Roman prefixes, and some of them come from the names of other chemicals. Like the first prefix that we're going to see is the much maligned prefix meth, which is associated with illegal drugs, of course. But actually, the prefix meth comes from the name of a compound called methylene, which means wine wood. So there's in a way you could sort of say that the word meth means wine, even though actually, ironically, we don't find it in most of our everyday wines. Okay, so meth, the prefix just means one carbon. If you have any chemical that has one carbon, it will have that prefix. So even though it has a really bad reputation on the street, it is not a bad prefix in chemistry. In fact, there are more chemicals that begin with that prefix than any other prefix, okay? Because they have one carbon. The prefix for two carbons you might not have heard of. It is eth. It sounds almost like I'm lisping, but I'm not. Okay, let's just take away the M. The third one is prop. You might have heard that one before. The fourth one is, careful how you pronounce it, bute. It's pronounced bute. Then we get to the ones that are more like the polygons. Pent is 5. Hex is 6. You probably know 7, right? Don't you? What's the prefix for 7? What is that 7-sided polygon called? What is that called? Oh yeah, a heptagon. What? Okay, hept is 7. And then oct is 8, well, like October. Non is 9, almost like November. And dec is 10, like December. So these are the ones we're going to concern ourselves with. These are the most common ones, especially the first 5. Those come up all the time in chemistry because we get very commonly chains of 1 to 5 carbons. And then the ending, now this is just a prefix, by the way. So we need an ending. So I'm going to show you the first group of hydrocarbons, which uses these prefixes, and then it has an ending, a suffix that is added to it. By the way, I wasn't kidding about the polygons. Technically, a triangle can also be called a trigon, ask Raven. A square or a quadrilateral can also be called a tetragon. We don't say that very often. Then we have pentagon, of course, hexagon, of course, heptagon. The reason you don't hear much about heptagons is they don't quite look right. They sort of bother people. Look at that heptagon. Doesn't it look kind of wrong somehow? So for whatever reason, people are fine with the pentagon, but not so fine with the heptagon or the nonagon. Forget about the nonagon. Octagons are fine. We see those in stop signs. And let's see, nonagon, decagon. You may have heard of those. So polygons, just like our school so cleverly was named after, well, it wasn't named after it, but they used the pun repeatedly for like the polygon itself instead of the quad. Okay. By the way, that was originally meant to be funny, but some people don't get it anymore. And all the shapes that we find at our school, the orientation of the buildings, which they are changing with the reconstruction. But anyway, based on the polygons. So that might help you remember at least 5, 6, 7, 8, 9, 10, 5 through 10. The first group of organic chemicals that we are going to learn about, the most important group, I will definitely say, is called the alkanes. The alkanes. Now, it's very important how you pronounce this. So listen to how I'm pronouncing it, alkane. All right? Later, you'll see why. The formula for an alkane, this is what we call the generic formula. Kind of like, you remember when we saw the Vesper forms and it was like AB4? Well, it's kind of like that, although in this case it specifically has to be carbon and hydrogen, so we can use the actual symbols of the elements. So in this case, it's Cn, that means whatever number of carbon you have is N, H2N plus 2. So whatever number of carbon you have, you double it times 2, and then you add 2 more, and that gives you the number of hydrogen. Get it? So in other words, if I had 1 carbon, if N was 1, then 1 times 2 is 2, plus 2 is 4. So it'd be C1H4, that's CH4. Okay, and then we'll look at some other examples when C is a larger value. These are called the alkanes, and these chemicals are the only ones that are what we call saturated. Saturated is a word that comes up a lot in science. Being saturated is being fully loaded with something. In this case, the carbon chain is completely coated or loaded up with hydrogen. It has as much hydrogen as it can take. That probably won't make any sense until you get to see something that is not saturated. So just bear with me. It will make more sense when we see something that is not saturated. Let's look at some examples. The first one, the first alkane, with a chain of 1 carbon, is methane because it has 1 carbon, prefix meth, and it's an alkane, so that gives it the ending, the ANE ending. So put those together, you get methane. Methane is a very common chemical. And remember, in Vesper form, this is the way that we understood molecular shapes. You should understand the shape of this molecule because it has 4 pairs of valence electrons. They're all in the bonds around the carbon. They're all contained in bonds, and they push each other as far apart as they can, making a tetrahedron. So remember that a tetrahedron is the 3-dimensional form. That was a Lewis structure that we saw there that doesn't show the shape, but you can figure out the shape by looking at the Lewis structure. So again, this was an AB4 tetrahedral molecule, and it's basically what carbon gets if it gets coated with hydrogen. And of course, hydrogen is the #1 most abundant element in the universe. So if you're going to bond to something, that's probably what you're going to bond with. Natural gas is actually a fuel consisting primarily of methane. It turns out they're not too picky when they pipe the gas to your stove or to the Bunsen burners. They're not too picky about keeping everything else out. So I can't say that it's entirely methane, but the vast majority of it, well over 95% of it, is going to be methane. So if you wanted to picture what is that stuff coming out of the stovetop, if you have gas stoves, not of course for electric stoves, and in a Bunsen burner we use in chemistry labs, that is natural gas, that is methane. That is a hydrocarbon. So methane has that beautiful tetrahedral form, like a 4-sided die from Dungeons and Dragons. And imagine that is a gas. Imagine it's very, very lightweight, bouncing around. Methane gas, try to picture those little tetrahedral molecules colliding with each other, colliding with the sides of the container, or if they're in a room, colliding with the walls. That's how I want you to start picturing these lightweight molecules. We're going to need to start picturing their motion, even though we can't see it. All right? So that's what methane gas is. It's a good one for picturing gas movements because it's easy to picture that little tetrahedral form bouncing around. So the next one with a chain of 2 carbons with the prefix eth for 2 and the ending ane because it's an alkane is ethane. Now if we look at that formula, that generic formula, CnH2n plus 2, well now N is 2. Carbon, there's 2 carbons. So if we If n is 2, then double n, 2 times 2 is 4, plus 2 more. Oh yeah, we get 6. So we get C2H6. That is the formula for ethane. Ethane is also a gas. There is a little bit of ethane in natural gas as well, not as much as methane. And it is also a hydrocarbon. It's also an alkane. When we see the structure of ethane, it's interesting. It looks like almost like two tetrahedrons that have sort of smashed into each other. It's got an interesting structure. Then we come to one you've probably heard of, propane. Why is it prop? Because meth, eth, prop, there's 3 carbons. Why is it ane? Because it's an alkane. It's saturated. What's the generic formula again for alkanes? What's the generic formula for these again? Oh yeah, CnH2n plus 2. By the way, that's a propane tank, and propane is also used in hot air balloons. It's one of the gases that is used to heat a hot air balloon. So now we have 3 carbons. So n is 3. So it's 2n plus 2. So it's 2 times 3, which is 6, plus 2 more, which is 8. C3H8. That is the formula for propane. Now, propane is a gas at room temperature. But if you pick up a propane tank, and if you tilt it, you'll hear some liquid sloshing around in there. So you might be tempted to think of propane as a liquid. Well, it's only a liquid under extremely high pressures. They pressurize that tank like you wouldn't believe. That's why it's such thick metal. Under very, very high pressures, gases can be turned into liquids. But as soon as the gas comes out of that tank, you may notice that it comes out in the form of a gas. Okay, it is no longer a liquid. So that is propane. Propane has an interesting shape as well because of the carbon chain. Now notice there's 3 carbons in a row. The ones on the end are holding 3 hydrogen each, but the one in the middle is only holding 2. Interesting, because it's bonded to the carbons on either side. That is really why there is that formula, H2n plus 2. It's easier to show you in a Lewis structure, so let's look at the next one. Here we see butane. Remember, it's meth, eth, prop, butes, and that's a chain of 4 carbons. Here you can easily see the pattern. I forgot to mention that Lewis structures for hydrocarbons are so easy because carbon, all of its valence electrons go into bonds. Hydrogen, its only valence electron always needs to go into a bond. So what you wind up being left with is every valence electron for the entire molecule winds up in bonds. You don't have any pairs that are not bonded, any unbonded pairs. So butane, let's see that formula. Oh, by the way, so why is it 2n plus 2? Well, notice how each carbon has a hydrogen above and a hydrogen below, right? That's 2n. But then eventually you're going to reach the end of the chain. And so there's a hydrogen on the right side at the end of the chain over there. And then eventually you're going to reach the other end of the chain. That's the left side. There's a hydrogen over there on the left. Those are the plus 2. So no matter how long this chain gets, you'll still have the 2 that are on the end, right? The left and right, that's the plus 2. And you'll still have a hydrogen above and below every single carbon. So that's why it has that formula, 2n plus 2. That's why it has this formula. So now n is 4. Does everybody get what I'm talking about now? Cn, that means there's 4 carbons, right? That's the count of the number of carbons. So what's 2n plus 2? Think about it. 4 times 2 is 8, plus 2 more is 10. C4H10. That is the formula for butane. And of course, butane is also a gas at room temperature. It's what we call lighter fluid, but again, under high pressure. And it comes out, we often have these in little handheld lighters. Okay, butane is one of the active ingredients in there. But of course, if it's let outside, it's a gas. If it's let outside of its container, it is a gas. And butane, you can start to see the sort of zigzaggy pattern that occurs in these organic molecules. And if you blur your vision, if you blur your eyes just a little bit, squint your eyes, and look at that, don't you sort of see the edges of hexagons there? I can see it. Looks like there's an edge of a hexagon at the bottom and there's an edge of a hexagon at the top. It's almost like we're seeing parts of that hexagonal structure that we talked about before, like the structure in graphite. And it does kind of look like that. If you look at organic molecules, they tend to have that sort of what I like to call honeycomb form, that sort of hexagonal pattern that keeps repeating. Just in case you're not sure what I'm talking about, here is a picture of a honeycomb pattern. This is from a beehive. It's just a very efficient way to store your honey. And by the way, bees get a lot of credit for making honey, but really all they do is they transport nectar, because nectar from a flower is pretty much honey. They just modify it very slightly, they dehydrate it. So I'm not saying bees are bad. I mean, bees do a lot of pollination, but they get a little bit too much credit for making the honey. It's more like they transport it. Anyway, those are the end of the notes on organic chemistry, but there's a lot more that we need to go into. We're still only going to scratch the surface, but we're going to go into some of the other hydrocarbons and then some of the other organic chemicals that can form. See you next time.